Hi, it's Mr. Anderson, and this is Chemistry Essentials video 47. It's on heat exchange. If I were to say, don't touch this iron right here in the middle, it's hot, what does that mean? Well, we know that it has a higher temperature, and therefore it has a higher amount of average kinetic energy. And if you were to touch it, a lot of that energy is going to be transferred to your hand. And that's going to produce quite a bit of pain. And so if we ever have a warmer body and a colder body, the warmer body is going to have more kinetic energy. And again, that energy is in the molecular motion, or those molecules moving around. And we're going to have more energy in that than the colder body. And so a good good way to represent that, and I'll use this model over the next few videos, is just using these little cubes that represent the amount of energy. In this case, that's going to be thermal energy. And so if I were to put those two objects in contact with one another, that energy is going to be transferred. In other words, energy is moving from that first object to that second object, and we call that transfer heat. And so what we're really doing is transferring energy as thermal energy, or heat. Now heat, if you were to look up heat on the periodic table, you're simply not going to find it there, because it's not a substance, it's not a thing, it's just the transfer of energy. And so a good way to think about that, and this should be a sentence that should kind of roll off your tongue: energy is being transferred as heat. That's really what's going on. And so when we're looking at energy being transferred as heat, it's going to vary depending on the substance that we're dealing with. In other words, metals are going to transfer energy through heat more readily than things like wood or brick. So let's look at this PHET simulation. So I've got iron, I've got brick, and then I've got water. And so we can assume that we have the same amount of each of these. And if I were to put the water on top of a heating device and the iron on top of a heating device, and I were to just increase the amount of energy, what I'm going to see is an increase in temperature. Well, what's really going on is that we're speeding up those molecules. That's speeding up the molecules of the thermometer. It's spreading apart. Likewise, when we cool it down, what we're doing is we're cooling down those molecules, cooling down the molecules of the thermometer, and therefore it's going down. But we really don't see that energy transfer as heat. And so now what we're going to do is we're going to click on the energy symbols button. And now we're actually going to see that energy inside those molecules. Now as I'm heating it up, what's really happening is I'm adding energy. I'm adding energy to that iron. Now you can see that some of it is being transferred out to the environment through heat. Likewise, when I cool it down, what I'm doing is I'm actually transferring that energy as heat into the ice cubes. So they have lower kinetic energy. What happens if I take that iron and I just throw it into the water? You can see that since it's hotter, it's transferring some of that energy as heat as well to the surroundings until it eventually reaches what we call equilibrium. And so if you ever have a warmer and a colder body, that warmer body is going to have a higher amount of average kinetic energy. And remember the Maxwell-Boltzmann distribution shows us how that works. If we were to look at it, this would be the cold body and this would be the warm body. Now in each of those bodies, they're going to have low energy particles and really high energy particles. But in the warmer body, that average kinetic energy is going to be greater. And so if we ever put them in contact with another, there's going to be a lot of collisions between these molecules. And as they collide, they're transferring some of that kinetic energy. And so what we're really doing is we're transferring energy from the warmer object to the colder object through heat until they eventually reach what we call thermal equilibrium. And In other words, it's the same average kinetic energy on both sides. And that picture I showed you of iron at the beginning, eventually what's going to happen is all of that iron is going to have the same amount of kinetic energy because we've transferred that energy out. Now, it's not the same for every substance. And so we use a term called specific heat capacity to measure that. And so right here you could imagine we have a kilogram of gold, a kilogram of aluminum, and a kilogram of water. And let's say that they're all in a container. And so if you look at it, they're going to have different amounts of specific heat capacity. If we look at the units, that's joules, which is a way that we measure energy per gram, and then Kelvin or degree Kelvin. And so if you have something that has low specific heat capacity, that means it's going to be changed. The amount of energy it has is going to change more readily than something that has a higher specific heat capacity. So let's add a little bit of heat to this and watch what happens to the thermometers. And so the gold, the aluminum are heating up more readily than the water. Now the energy is going to be the same. It's just that the water has a higher specific heat capacity, and so it's able to absorb more energy before it starts to change its temperature. And so did you learn to explain how heat exchange is due to kinetic energy transfer due to molecular motions? If you did, you learned